Welcome and thank you so much for tuning in. We're pleased to have you join this interagency working group on ocean acidification webinar. The title of today's presentation is Why are there so many pH scales for measuring seawater pH? And what do these scales mean for measuring or using seawater pH? This webinar is hosted by the Interagency Working Group on Ocean Acidification, a collaborative working group of 13 federal agencies that aims to coordinate and foster federal research and monitoring on ocean acidification. The group is chaired by Libby Jewett, Director of NOAA's Ocean Acidification Program. By hosting webinars, the Interagency Working Group on Ocean Acidification hopes to build the nation's capacity to work on ocean acidification and the community of people doing so. I'm Shallon Bush, an ecologist with NOAA's Ocean Acidification Program and Northwest Fisheries Science Center in Seattle, Washington. I staff the Interagency Working Group on Ocean Acidification and will be monitoring today's session on behalf of the group. Jen Bennett-Mintz, Education and Outreach Coordinator for NOAA's Ocean Acidification Program, is also on the line and will be helping to facilitate today's session. During the presentation, all audience members will be in listen-only mode. You're welcome to type questions related to technical issues or for a presenter into the questions box in the bottom of the control panel on the right side of your screen. We'll be monitoring incoming questions and will respond to them or pose them to our speaker. We are also recording this session. A video recording and PDF of the presentation will be available in the future and linked to on the group's website. We're very excited to welcome our speaker, Dr. Andrew Dixon. Dr. Dixon received his PhD at the University of Liverpool in the United Kingdom in 1978, studying acid-base chemistry in seawater. After a postdoctoral fellowship at the Marine Biological Association Laboratory in Plymouth, modeling chemical processes in estuaries, he moved to the University of Florida to work on a project aiming to define pH in seawater. In 1983, he moved to the Scripps Institution of Oceanography at UC San Diego, where he is now a professor of marine chemistry. His research focuses on improving our understanding of the CO2 system in seawater, with a current emphasis on the effects of ocean acidification. And with that, I'm going to pass the presentation over to Andrew.
Hello, everybody, and welcome. So, the title here perhaps promises more than I can fully achieve. And the bad news is that the content is perhaps more complicated than the title. We really have trouble with pH scales, and in part, these quotations that I'm going to show now really point out why. It's a historical problem. Over the years, people have developed ways of measuring pH in seawater and of calibrating those pH measurements. And it's only now that we're trying to really understand exactly how that fits and how we can improve it to make it results with smaller uncertainties. So in addition to this classic quote, you should perhaps remember the sort of later follow-on. The first time it repeats as tragedy, the second time as farce. Let's see the extent to which that might or might not be happening in thinking about pH scales in seawater. So, during my PhD, and as you heard there, that was many years ago, I started to develop an interest in this and wrote, when I first was at Scripps, this paper summarizing the situation. And I had this introductory sentence pointing out that the field of pH scales is one of the more confused areas of marine chemistry. Now that's 32 years ago. Of course, by 2011, it could be written again with the phrase, 27 years later, it still remains confusing. And even in a paper this year, my co-authors dragged this back out again and pointed out that despite the progress, several mutually inconsistent conventions are used to estimate pH from measurements. Now, in principle, of course, one could write a book on this. So what you're going to hear in the coming presentation is a much more restricted subset to just give you a flavor of what's going on. We'll address particular things in the questions, and if you have further questions, I'm sure that you could find my email and write to me, and in the fullness of time I will try to reply, providing I can reply promptly and reasonably short. So the definition of pH, if you look it up in multiple books and recent documents from the IUPAC, is typically like this: minus the decadic logarithm of the activity of a hydrogen ion. But as is pointed out here, you can't actually measure that. So although you can define it, that is, write it down, you cannot measure what's there. You need some kind of additional information to get a pH measurement. And that's really where the problem starts. The initial definition of pH had it in terms of the concentration of hydrogen ion, and it came to be recognized very quickly that this was not an adequate definition when you were talking about multiple different aqueous solutions, and that to think about it as the activity, or in those days thought of as a kind of apparent concentration, made a lot more sense. The measurement of pH is typically an electrode, a pH electrode. You'll buy one. It's a combination really of two electrodes, a reference electrode, often sensitive to chloride ion, and an electrode reversible to hydrogen ion, typically like a glass electrode. And this electrode system dips in your test solution where the electrode reversible to the hydrogen ion is touching the test solution here. The reference electrode is in the potassium chloride solution, and there's a liquid junction defined by these two lines here between that reference electrode compartment and the test solution itself. The EMF of this can be written in this form: a standard potential, something to do with the chloride concentration which the reference electrode is measuring, something to do with a liquid junction potential between the two solutions. Essentially, when you have two solutions of different composition diffusing into each other, that diffusion is in part causing ions to separate and creating a potential, and that's the liquid junction potential, and then the term inactivity of hydrogen ion. So more simply, we hope that everything in these parentheses is a constant and can express it with this much more simple looking expression. So if we take the difference between the values of the potential measured, of course, at the same temperature for two solutions, the test solution that you care about and some standard solution, you can look at this equation and say, okay, I could write down a difference. And the difference will give you the pH, or this term, for the test solution, and in terms of the value for the standard solution, the difference in potentials that you measured, and any difference in these liquid junction potentials. Comparing those two equations, this and the more usual definition of pH, where we can see the similarities here, for this pH to be equivalent, you need an activity in this standard solution. You also need this liquid junction term to disappear. The activity in the standard solution is one that a lot of people put a lot of effort into, probably from about the 1930s through until the early 1970s. The set of buffers that you can buy at the moment, the phosphate buffers, the borax buffers, the phthalate buffers, were all calibrated using a particular cell referred to as a Harned cell. It's a very useful cell because it measures the properties of HCl in a way that has no liquid junction. and the EMF is just dependent upon the activity of hydrogen ion and the activity of chloride ion. And so we can rearrange that expression to give this so-called acidity function. And we can see, therefore, that at any point we can measure this grouping with the activity of chloride directly. If we can give a value for the activity coefficient of chloride ion, we get a value for the standard potential. That's the approach that underlies giving pH to commercially available low ionic strength buffers. The difficulty is that that number is people's best guess as to what it might be. And then in the 1960s, people agreed that their best guess was probably good enough, and they formalized it as a conventional value that says, we assume that the activity coefficient of chloride related to these buffer solutions has this particular value. Of course, how well does this work for seawater? Well, go back here to this expression, and we've got three main problems. First, the activity of hydrogen ion in those calibration buffers is not known perfectly because you've got that conventional activity coefficient for chloride ion. And realistically, if you buy a buffer, let's say from Fisher Scientific or some chemical company, almost certainly they didn't calibrate it using a Harned Cell. They calibrated it against a buffer that maybe had been calibrated using a Harned Cell. And there may be this whole chain of comparisons leading back to a value given by a national metrological agency like NIST. So there's an error in that term. The residual liquid junction potential, that is, this difference between the liquid junction when the solution here is seawater and when the solution here is your standard buffer, so this difference here is not zero. It's a number of millivolts. Worse yet, it's not a consistent number. If you have a different commercial reference electrode, you will almost certainly get a different residual liquid junction potential. Which means that if you measured the pH of seawater with 4 different electrodes really carefully, you should reasonably expect 4 different values for pH. This is problematic. And this really has been one of the reasons that there was a need for a change moving forward, when people realized, probably in the 1970s, that this was true. So this so-called NBS pH scale is when the pH of seawater is measured in this fashion. That's using a pH cell together with some low ionic strength buffers. It's often referred to as being on the NBS scale. NBS was the National Bureau of Standards. They changed their name in the 1980s to the National Institute of Standards and Technology. It's the metrological agency for the USA. Strictly, these buffers are particular standard reference materials obtained directly from NIST. But as I said, more typically, they're at best traceable to these primary standards and consequently a larger uncertainty. But it's this problem with the liquid junction that really is the damning problem for using this NBS pH scale in seawater. It depends, the variability depends on the design of the liquid junction. Some are better than others in terms of how stable they are, but different designs come up with different potentials, and thus, in principle, different apparent pHs. As a result, in the late 60s, people said, well, look, there's another way around this. In solution chemistry, where we're studying reactions happening in background solutions like sodium chloride or sodium perchlorate, we don't measure pH calibrated against these buffers. We try to come up with a measurement of the hydrogen ion concentration in our solution. And in principle, you can use this same pH cell, but recognize now that EMF can depend on the hydrogen ion concentration, where that term E star is only a constant if the activity coefficient for the hydrogen ion doesn't change during your experiment. So the assumptions are that this term is constant. Typically, it will be a function of temperature and pressure and solution composition. So the key here is the solution composition cannot change much in order for it to remain essentially constant. And this residual liquid junction term is also assumed to be small and a function of changes in the composition. Most typically, changes that substantially change the conductance of ions, that is, changes with regard to hydroxide ion or hydrogen ion. Also, this expression assumes that your pH cell is behaving ideally. That is, it has a Nernstian slope, that is this RT over F term here, which forms from basic thermodynamics for electrochemical cells, and no drift. That is, the idea that this term here is a constant that does not change with time. So we can measure it at one point and use that value at another time. That's not so realistic. These electrode calibrations, when you look with a kind of microscope, do change with time. And so the approach taken in solution chemistry would say, okay, if we actually can do this in the middle of a titration, we can measure the E star as close as possible to when we need to use it. And the approach taken is to make solutions of known hydrogen ion concentration, which in a simple sodium chloride solution, you could imagine if you just added HCl to the sodium chloride. And you can calculate then immediately what the hydrogen ion concentration is, because it's the mass, the weight of HCl and its concentration over the weight of HCl plus the original weight of the solution. Very simple dilution. If you know the hydrogen ion concentration, and if you can assume that you know this or that it's zero, you measure EMF, you've measured E star. If you do this in a titration, you get multiple points where you can average the result. So the assumptions here are that the activity coefficient of hydrogen ion doesn't change during this titration. And the usual approach is to say, okay, it's most constant if we don't change the ionic strength. So we add either hydrochloric acid at the same concentration as the sodium chloride, or we add hydrochloric acid in a sodium chloride background so as not to change the ionic strength and keep that activity coefficient constant. Now, experimentally, people have found that in these titrations, this term is some function, linear function of the hydrogen ion concentration, and it can be typically ignored if the hydrogen ion concentration is less than about 1 millimolar. That is about 10 to the minus 3 moles per kilogram of solution. And so it's often the case that people calculate this E star at the same time as they're doing a titration. Those of you that know the titrations for total alkalinity will recognize that that's inherent in the way the data are processed. It's also inherent when people are using titrations as a way of investigating equilibrium constants for acid-base processes. The basic idea is if there's this large ionic background, the other species may change in concentration, but there's a very limited change in the activity coefficients. Again, you either need to ignore this residual liquid junction potential change or know something about it. So how well does this work for seawater? Because this was the idea. Well, we could just get away from these low ionic strength buffers. And the problem with seawater is that it's not sodium chloride. It's a much more complicated solution, and a lot of work's gone into measuring the composition of it. A simplistic view you can see here. Seawater, of course, is mostly water, about 3.5% salt. The salt is chloride ions, sodium ions, sulfate ions, calcium ions, potassium ions, magnesium ions, and everything else. Everything else is less than 1% of the total dissolved salts. So the other part that we know about seawater is that the proportions between sodium and chloride, or sulfate and chloride, or calcium and chloride, or potassium and chloride, magnesium, remain constant around the ocean, because what mostly seems to happen is we add or remove the water, from making it a higher salinity by removing water, or a lower salinity by adding water. So this constant relative proportions suggests you can think of seawater as an ionic medium of a particular composition. And this was the approach that was taken to study reactions in seawater. Simple synthetic seawater medium containing just sodium, potassium, magnesium, sodium, potassium, magnesium, and chloride and sulfate. We're leaving out the CO2, the boric acid systems, and replacing constituents such as strontium and alkalinity and fluoride and bromide to keep it at the same ionic strength. There's a key assumption. The activity coefficients of reacting ions in this synthetic seawater medium are believed to be the same as they would be in natural seawater, and to remain essentially independent of variations in the low concentration of these reacting species. There's a problem. There's always a problem, right? Sulfate ion. Sulfate ion reacts with hydrogen ion, but it was also one of your medium species. It's actually about 3 millimolar in seawater. It's also got large dissociation constant. And so it's a difficult dissociation constant to measure accurately. The approach that was taken was to define this total hydrogen ion concentration, where the total hydrogen ion concentration is the sum of two terms: the free hydrogen ion, that is, the hydrogen ion that's not reactive with sulfate, and an estimate of what's reacting with sulfate. Now, there's a subtlety in this expression. A simple way of thinking of total would be say, okay, it's the free and the bisulfate. But as you add more and more acid and get more and more bisulfate, then the relationship between the free ion and the bisulfate ion changes slightly. By defining it, and this is just a definition, a total hydrogen ion concentration in this way, this term, where total sulfur and an equilibrium constant, is purely dependent on this. So we get that the total is a linear dependence on the free. That means it's going to work properly for pH cells. And we can rewrite our expression for a pH cell, where now there's this whole term in brackets that is our equivalent to a standard potential, and still works perfectly well. But now we're already up to 3 ways of thinking about hydrogen ion. One, this activity of hydrogen ion that we tried to get as a pH measurement against carefully designed buffers, or the idea of just a free hydrogen ion concentration, which we could think of sensibly for sodium chloride medium. And then now we complicated that to say, well, how about a total concentration in seawater medium? The successful calibration, though, still requires this same problem. In order to calibrate, you have to know the known total hydrogen ion concentration. Now, there are two ways of doing this. One, these are based on acidometric titrations. That's similar to the sodium chloride in that for each amount of HCl you add just to pure medium, you can make an estimate of what the hydrogen ion concentration is. And if you know roughly what that equilibrium constant K is, it's actually a very, very good estimate. More recently, instead of doing it by titration, we've used the Harned Cell to calibrate buffers in synthetic seawater. These are called tris buffers. And again, we end up with something that's related to a pH. It's actually the ratio between, it's, just making this a dimensionless term in order to take the logarithm. K naught is just 1 mole per kilogram of solution. Another term, which is an experimentally available term, you measure an EMF with that Harned Cell, you measure a chloride concentration. There's an experimentally determined calibration. The inside of these brackets would be another 30 minutes on this talk, so this is going to be long enough. I'm throwing that away. And this last term, activity coefficients. Typically, that's assumed to be 0. That is, you're basically saying that when we replace some sodium chloride with tris and tris HCl in these buffers, we don't change the activity coefficient of HCl. That's not strictly true, and work is going into ways of improving on this, either with a model for activity coefficients or some empirical ways of extrapolating it to the point where that really is true. Leave that for now. So what pH scales have we discussed so far? Well, really we've discussed two. The NBS, which the uncertainty is not well defined, and the uncertainty, and it's electrode dependent, and the total. The total scale includes this bisulfate ion implicitly. It has perhaps the lowest uncertainty practical using buffers based on the Harned Cell. Now, there are two other scales that you will see all the time mentioned, but really they kind of build from these. First is this free scale. It's a simple concept. What it says is, well, let's explicitly include bisulfate or even hydrogen fluoride in natural seawater. But to do that, you've got to have a good equilibrium model. And we don't know at the moment how uncertain our equilibrium model is for doing this. And so there's an error that's bound to be there, but we're not sure how big it is. There's another one is a seawater scale. This one implicitly includes the effects of reacting with sulfate, but also another ion in seawater, fluoride, which forms hydrogen fluoride. We don't have the fluoride in our simple synthetic seawater. But if you were doing a titration in a natural seawater, then you would have fluoride present. And it's from the days that people were trying to get equilibrium constants from titrations in natural seawater that this really is there. And it too will have a reasonably low uncertainty, but it comes from titration, so it's probably not as good as the uncertainty based on Harned Cell measurements. And it's also got an uncertainty due to the fluoride, so that's probably a little bit bigger. But just a moment. I mean, we've spent so much time talking about pH, but we don't really. Why would we care about pH? It's because it's something we can measure. But really, for most of our work, we want to use it in equilibrium calculations. So for acid-base chemistry and aqueous solutions, there's a quick summary here. Equilibrium constant for that reaction is this. Oh my God, you say. Well, we'll get on with that. The equilibrium constant is traditionally a term in concentrations and a term in activity coefficient. That is really, it's based on the activity of hydrogen ion times the activity of the acid, the base coming from this acid, divided by the activity of the acid itself. And we can group all these activity coefficients together in this one term with a capital gamma. And I'll just use that as a simple notation going forwards. Now, the activity coefficients are functions of temperature, pressure, and solution composition. This K was just a function of temperature and pressure. If you wanted to use this, you've got to calculate some kind of speciation. So if you can measure a pH, and we'll talk more about this, but for most of these things, the hydrogen ion concentration is 10 to the minus pH divided by some arbitrary constant. It's not an arbitrary constant, by a constant that depends on how you defined your pH. Ideally, the constant will be equal to 1, but the ideal is rare. So in this case, you can again calculate the speciation for your acid-base system. And the problem is you need to know a lot of things. You need to know the pH, and you need to know that constant. You need to know the total concentration, you need to know the equilibrium constant, and you need to know this activity coefficient term. You really don't know that activity coefficient term. Surely they were never this complicated. Well, they are, but we hide it from ourselves. In seawater media, that activity coefficient term is a function of salinity, temperature, and pressure. That is, I said it was a function of composition, temperature, and pressure, but in seawater, we have this simplified version of composition, which is just salinity. As a result, we can define an equilibrium constant purely in terms of concentrations, and you can see that that's calculable from the previous equilibrium constant. And we can hide C. So if we're calculating the ratio between the base and the acid forms of the dye, of any acid-base species, it's the ratio between the K and the hydrogen ion concentration, or the K, 10 to the minus pH over C. Rearrange that. And we could just include that C directly in the K. And in principle, that's usually what happens. Of course, if you calibrate your electrode at the same time as you're measuring an equilibrium constant during a titration, that C is hidden in that K directly without you ever even thinking about it. But the problem is that depending on how you define and measure pH, the value of K, this K star that you need to do this calculation, will change. So we do this in ocean water. We define these stoichiometric equilibrium constants. And for these calculations to be as accurate as possible, the pH and the K must be defined, as far as is practical, on the same pH scale. So the pH scales are kind of related to one another, which is helpful in most cases, but this is what makes it so confusing. You go, gee, what am I really doing here? As I said, with the NBS pH scale, this constant is an empirical electrode-dependent term. So you can't just calculate it. You need to measure it somehow. If you measure it, then it's usually a value around 1, and expressed as delta pH, that's a delta pH of around 0. But the uncertainty, because you have to measure this, is actually quite large, about 0.02 in pH. If you want to calculate this term, it will have a value of about 0.1 expressed in a pH form, and the uncertainty is about 0.01. For the free scale, ideally this is equal to 1. It's almost a definition, so there's no real uncertainty. With the seawater, it's a slightly difference, about 0.01 different in pH, about the same uncertainty. So what does this mean? Well, worst case, it means that you can screw up that relationship by the equivalent of about 0.12 of a pH unit by using the wrong constants for your pH scale. That means you're messing it up by about 25%. Probably some of you would believe that would matter. If so, don't do it. Ask yourselves, how am I measuring pH? Which of these scales am I choosing? And as I said, probably you're going to want to choose a total scale. So conclusions are fairly straightforward. For marine systems where pH can be measured on the total hydrogen scale, I say S greater than 20. That's currently based on how easy it is to make a simple tris buffer that you would calibrate and understand well, or that you could use somebody else's calibration based and through a spectrophotometric pH such as metacresol purple. Also, there are good equilibrium constants up down to about salinity of 20, where we have a reasonable understanding of their uncertainty. So ideally, if the salinity is greater than or equal to 20, it's probably most accurate to use the total scale, total hydrogen ion concentration scale, with appropriate equilibrium constants. In all the computational packages, such as CO2 calc, you get to say which pH scale you're using, and it will choose the appropriate equilibrium constants. This is convenient if you understand what you're actually doing. At lower salinities, it's less clear. Equilibrium constants have been measured that extrapolate to a salinity of 0, but there isn't really a pH calibration in that region that is as reliable as perhaps the equilibrium constants are. And so it's not so easy to get good data in that region. Now, a salinity of 0, ideally, you might link back to this original definition of pH based on low ionic strength buffers. Because the essential idea of having a low ionic strength buffer to measure a low ionic strength solution was that the liquid junction potential was dominated by the effect of that potassium chloride. And so there was very small residual liquid junction potential because the two solutions were, the liquid junction was dominated by the much more concentrated potassium chloride. This wasn't true for seawater of salinity 35, but down at very low salinities, it's still true. And so there's still some research going on to say, okay, is it feasible to define seawater pH in a way that smoothly and correctly goes into this low ionic strength definition in a way that would work for the buffers there. So ultimately, I'm sorry I've taken so long to do this, but we're kind of going through here saying, okay, is there a better way to think about this? The key is to say, we have so many pH scales because they reflect two completely different paths to defining something to do with hydrogen ion. One, through establishing buffers where you knew the hydrogen ion property of the liquid and you could use that to calibrate a pH measuring device. The second, that you make those solutions kind of on the fly in titrations and calculate from that the properties that calibrate your pH measuring device. We end up, as a result, with these multiple pH scales, and the real difference is just how uncertain the inherent pH measurements are and how that ties back to the uncertainty of the equilibrium constants in any of the calculations that you want to do from then on. So to go back to the original title, why are there so many scales? It's a historical artifact, both tragedy and farce. what does this matter for you looking forward at the moment? You really have to ask yourselves, what am I measuring? What is it convenient to measure? And make sure that you do your best to choose equilibrium constants that match with the way you're measuring pH, so that your calculations have the lowest practical uncertainty. Anyway, thank you.
Thank you so much, Andrew, for that great presentation. So we're going to open the floor up for some questions. So please type questions or comments into the questions control panel. And we've had a couple questions come in already. And the first was from Jean Broder. And he said, thanks for the talk. In practical terms, in order to study the complexity of an estuarine or coastal system, we need to analyze waters with a wide variety of salinities and thus ionic strength. This makes the choice of scale non-trivial. It seems an even worse choice to use two scales than to use one like NBS that may later be refined and or converted into values on the other scales. Do you have suggestions for estuarine work?
I think the first point to recognize about most estuarine work is that for many scientific purposes, you can probably tolerate larger uncertainties there than people would like to do for open ocean studies. If you accept that premise, then you really say, okay, how can we do this? And if you're going to use a pH probe, like a glass electrode or a ion selective FET, you need a way of calibrating it which is based on a buffer. The readily available buffers are the ones that I refer to as the NBS buffers. Typically they're not NBS buffers, but these will have values like 6.86 or 7.4 or 4 or 9.1. If you separately said, okay, I can do a simple calibration of my probe to calculate that term C, then you would probably be able to do this all together. That would be my own personal view on this, but I have to admit it's not one I've tried a lot at the moment. Going forward, the problem with probes is that for many of them, they are not stable with respect to time. That is, the calibration drifts, and you have to go back and recalibrate. And so the real benefit of a spectrophotometric technique is that potentially the calibration is built into the chemical properties of the dye used. And a spectrophotometric technique still needs work to calibrate it from the range of salinity 20 down to salinity 0. I know of groups that are working on this to differing degrees, perhaps, of expertise and how much effort they're prepared to put into it. But ultimately, and perhaps quite quickly, I'm hoping some data will come available that would say, okay, the right way to do this is just calculate it on a total scale that works perfectly sensibly for an indicator dye system. The equilibrium constants are known for that region. Their uncertainty perhaps a lot less well known. The real problem is when you go down below salinity 5. Because when you go down below salinity 5, my simplistic statement, treat seawater as though it had one composition variable, salinity, starts to fall apart. And worrying about that is probably equally important to keeping the quality of the data up as worrying about how you measure pH. That is your equilibrium constant really any good? And so my comment, therefore, just to summarize, is I think that you could do a pragmatic approach based on using an NBS, but you would have to empirically get the relationship between hydrogen ion concentration and the displayed NBS pH. And that empirical work is relatively straightforward, but it's not well documented how to do it. Otherwise, you would use spectrophotometric pH measurements and hope that somebody else did the calibration. And people are working on this. There's already some published estimates. The uncertainties are perhaps quite large on the published estimates. So we're at the situation that there is no good answer. There will be another webinar in a couple of months where I talk more about equilibrium constants for estuarine range, and this will come back to discussing estuarine pH. So it will be a more focused possibility then.
Great, thanks, Andrew. So we have a second question coming in from Tom Oliver, and his question is, in seawater, hydrogen ions are likely to be interacting with a range of ions. So why are the sulfate and fluoride ions the most important for inclusion in the pH scales?
You're right. In seawater, there's multiple simultaneous equilibria, acid-base equilibria, with a whole variety of species. The carbonates, the borates, the phosphates, the organic acids, and many others as well. The choice of sulfate and fluoride is an arbitrary distinction of convenience, where we ask which are those bases that make up part of our ionic medium, that is, whose concentrations change purely proportional to salinity, and which ones would be in that background medium. And as I said, the simple medium of sodium, potassium, magnesium, and calcium with chloride and sulfate only has sulfate. A more extensive medium, say based on the standard reference composition of seawater, might conceivably also think of having fluoride in, though my own opinion is that you don't gain anything by including fluoride in the medium. You can treat it as a separate equilibrium. And so it's this distinction about, can we include it in the medium, or do we have to treat it explicitly as an equilibrium? And for the sulfate, it's advantageous to include it in the medium because the equilibrium constant is not very well known, and because the dissociation constant is quite large, as I said, about 10 to the minus 1 in seawater at 25 degrees and a salinity of 35.
Great. So if you're ready for a third question, Li Qing Zhang asks, what's the best software program to convert pH values from one scale to another?
If we go back to this table, I hope it's still displaying, but you will see that the conversions between the total, the free, and the seawater scale are all computational. That is, if you know the equilibrium constants and you know the total concentrations of sulfate and of fluoride, you can do that calculation. So all the software implements those and implements them sensibly. The relationship to the NBS is an empirical electrode-dependent term. The software is based on an equation which was published in, I think, around 1980, which referred to the electrodes that were being used then in the laboratories at Oregon State University, and it has a significant uncertainty associated with it. So that equation is also built into these software. So the software that I'm thinking of is either the CO2 sys, CO2 calc, or there's one in R, I forget the name of it, and one in MATLAB that do these calculations. They all implement essentially the same calculation. There is no reason to believe, because there's been extensive checking of this quite recently, that these are done, that the main calculations are done wrong in any of the software. So they're all equivalent. How they handle this NBS one has not been so scrupulously tested, to my knowledge, so I can't tell you that they are all equivalent. They should be all equivalent, but it's easy to have typos in software. So I don't have one that I say is better for this. The ones that are more convenient for you to use personally are the ones you should do, because saving yourself trouble when you can is always a good idea.
Good point, Andrew. And just the R calculations, that package is called CCARB in R. And I'm going to ask a related question. So if you're totally new to monitoring pH in seawater, is there an easy resource to find out what scale your equipment is measuring on?
It depends. Most equipment, you have to calibrate it yourself. If you calibrate it yourself, it's really your choice of calibration solution that determines what scale it's measuring on. In the case of the indicator dye methods, they are usually ultimately calibrated back, again, to a particular calibration solution, the tris buffer in synthetic seawater, and thus usually on the total scale. If somebody just says, oh, we have calibrated this instrument and it works, it's time to be suspicious. There is no easy way of saying, oh, great, thank you, now I know what scale it's on. Because another way that's sometimes used is people will put an instrument like a CFET in the ocean and then say, well, we don't really know how it's calibrated, so we'll do this, what my colleague Todd Martz refers to as a vicarious calibration. We'll sneak up beside it and we'll grab some of the water that it's measuring and we'll figure out what the pH of that water was. Now, there's multiple ways you could figure out the pH of the water, and you could do it by measuring the alkalinity and the total carbon, and calculating the pH. Now the pH you calculate will depend upon the equilibrium constants you chose, and what scale they were defined on. Also, it's going to have a significant uncertainty because there are uncertainties in those equilibrium constants, let alone your measurements. Or you might say, well, and I'll measure the pH in that with a spectrophotometer. Well, that works too. Goes back to my comment about mostly those are on the total scale. The difficult part is making sure that you calibrate at the same temperature as the water was being measured on your instrument. And so sadly, there is no simple answer to doing this. This history of tragedy and farce tangles in a way that will continue, I think, for probably another, we like to think that when we have a good idea, it replaces everything else, and the answer is it does, but the time scale is usually decades.
Okay, great. So I have more of a philosophical question now. Could you talk a bit about how people's using of these various scales of pH has influenced our understanding of OA? So, I mean, another way to think about this is what could people's naivete to the implications of the various scales, what could that mean to our understanding of the progression of ocean acidification?
Well, here in all this, there's a discussion, which is what is your scientific problem and what uncertainty do you require in your measurements in order to make progress with it, understanding that scientific problem, compared to, and what is the uncertainty in your measurements. So if your goal is simply say, okay, I've put an organism in a seawater, and I put its friends and relatives in a different seawater, with a different pH, and I've measured the pH in the two seawaters, and the ones in the lower pH are not doing so well as the ones in the higher pH. That kind of experiment is actually not too susceptible to problems with pH scale, because you measured the pH yourself both times and probably did it roughly the same way. And so the difference in pH is reasonably significant. The original pH, less so. As I said, you could be 25% wrong with the hydrogen ion concentration. Does that matter? I think it's fair to say that for many organisms, 25% is kind of on the ragged edge where you would notice they were really noticing it. In contrast, if you're looking at changes in the open ocean gyres and saying, aha, the CO2 that's supposed to be going into the ocean is going into the ocean and it's changing the pH, well, 25% is the total change since the beginning of the Industrial Revolution. So you really would have no way of feeling comfortable that you made measurements 10 or 20 years apart and saw a significant difference if you have that kind of error hidden in what you're doing. So those are the two sort of outside bounds of this. And the real difficulty is anybody has to say, look, I'm measuring pH. Why am I measuring it? How well do I need to measure it? How do I know I am measuring it that well? And those are the kinds of questions that you need to ask, because on the one level, even doing it quite crudely by modern marine scientists' opinion would be still give you useful information about how an organism is behaving in changing composition. On the other, if you're looking just purely to see a change in a location with time, you substantially degrade your ability to do that if you don't have a clear idea of what your uncertainty is and work to minimize it.
Great. So with that, I have to apologize if we did not get to your questions about the content of today's presentations. Feel free to contact Andrew via email, and you can find his email in the right-hand side of your control panel in the chat box. You can direct any questions about the Interagency Working Group on Ocean Acidification to me at shallon.bush@noaa.gov. And bear with me while I change.
And my email is also there on the cover slide here.
Great, thanks, Andrew. So thank you for attending this Interagency Working Group on Ocean Acidification webinar. We welcome any feedback, further questions, or suggestions for topics for webinars. You can submit this input by replying to the follow-up email you receive or by emailing us directly. A link to a recording of this webinar and a PDF of the presentation will be available on the Interagency Working Group on Ocean Acidification's website in the future. As Andrew noted, please recognize that he'll be giving a second webinar for the Interagency Working Group on OA this spring. The title of this second presentation is CO2 System Studies in Brackish Waters. What should I measure and why? And I'll send out details on this webinar in the future. So thanks again to Andrew for his very informative presentation, and to all of you for your thoughtful questions and taking the time to join us. This is the end of today's session.